Today, we have 3 parts. I will start with some world models in 2D and 3D, essentially how to represent a map. For the 2D, since last time we already have the passkey tutorial, I guess many of you already have seen the implementation in Rust. And today we will talk a little bit about the 3D mapping, namely the Connect Fusion and how Connect Fusion represents a map in 3D. Finally, I will talk about the continuous. That's an extension of the Connect Fusion. From last time, you guys already have seen the Rust map server. We also have run a scenario AMCL. And also the G mapping. On our right-hand side, you guys must be familiar with this kind of probabilistic map. Like what's the probability of that grid as an obstacle? And essentially, the basic idea is to match consecutive frames of the LiDAR scan. So let's formally introduce occupancy grid for today. And it was introduced a long time ago, 1980s. You can see it at the bottom left. This is from a sensor, and you could see the z-axis. The average is about 0.5. So in the beginning, your occupancy grid has the probability of the obstacle about 0.5. But if you have a range finder, it could be LiDAR, it could be other range finder, you could generate. You could see the figure over here. As long as you have more confidence that the area in front of you is not occupied. And if you have multiple scans, like the right-hand side, you could incrementally merge those scans together. So you could see it on top, that's the initial scan. With multiple scans over time, those occupancy grids, each cell could be updated within each scan. We definitely want to know the pros and cons of the occupancy grid. You have, for example, a LiDAR, a rangefinder. You do not rely on any predefined features. The occupancy grid also offers the constant time access and provide the ability to represent unknown areas. This is very important, especially when the robot unknown environment and you want to do an exploration task. But on the contrary, disadvantage would be high memory requirements, especially that you want a very fine-grained occupancy grid. If you want high resolution of the occupancy grid, you will need even much more memory. And the second disadvantage is that because we have to cut it in grids, so the cutting maybe in some scenario is not clean, so that you will have some potential errors. Maybe the surface is not continuous. You need a discrete representation, so that will introduce some errors. Here comes a question. Occupancy grid, although there are some advantages, one disadvantage is the high memory requirements. So what can we do with it? Suppose you have a resource constrained mobile robot with limited memory, and you are not allowed to have a very high resolution occupancy grid running in your memory. Then what can we do? Definitely, we may want a different data structure to represent the map. So let me introduce the first type of alternative is the line map. Essentially, if we start from the bottom left, if we build a map from G mapping, for example, you will get some points. Suppose we limited this map in 2D, then you will have a few points over there, depending on what sensors you have. And then we already mentioned about some line fitting algorithms. For example, we can use a ransack. We could use a Hopf transform, for example. We could try to merge a set of points into a line. So suppose on the right-hand side on top, suppose we have maybe 50 data points. Then each one in 2D, we need to store X and Y. That would be 100 floating points. But now if we can use the 3 line segments to recover all the points, then we only need 6 points. That would dramatically reduce the required memory. So this is one way to go. Let me introduce you another one. It's called topological map. When we want to build a map, we could think about what's the task we want the robot to carry out. For the occupancy grid or for the line map, you could imagine that we just want to represent the obstacles, essentially the obstacles. And then later we could try different planning algorithms to allow the robot to move from A to B. If we think of the robot task, suppose we want to move the robot from one place to another in the map, we could actually build a map specifically or a perfect, very feasible for this task. Here, we could use a graph to represent this map. And the idea is that we want to build this graph so at each edge or vertices, it's away from the obstacles. So that's the basic idea. This example, actually, we have introduced the algorithm in our tutorial in Jupyter Notebook. Suppose we have 4 obstacles in the map, and we want our robot to move and try to avoid those obstacles. And actually, we could try to build a graph for it and try to find the vertices and edge. That's away from those 4 points. You could take a look at, for example, those 2 points. The easy way to do it is to get a vertical, get a perpendicular line over here. And suppose we get the other 2 points, we get another perpendicular line and the third one. We could actually draw those edges and get the vertices form this graph. For example, the distance from this point to this one and this one are actually the same. So that we could build some cells and the segments in order to form a different map in order to be used by a robot for a path planning task. Okay, and actually this method has been used quite commonly in robotics. The next map, we call it landmark-based map. From the right-hand side on top, and we could see that there are a few circles in the map. And then those circles are actually rocks. You could see it in the image. And the basic idea for landmark-based map is that the landmark is locally distinguishable features. In other words, we want something unique in the environment so that our vision could detect it in every single frame. And when we see it from different angles, we could actually get a measurement from where we are. The good things about landmark-based map is that we could solve inevitable uncertainty of the robot. So the robot maybe start from t equal to 0 and t equal to 1, 2, 3, 4, 5. For example, use the visual inertial odometry or visual odometry. But without the loop closure, the uncertainty will increase. The loop closure is the way to solve this problem. And this also comes with a line of research called place recognition. So researchers have been trying to do this loop closure when the robot comes to the second place at different time. You could see on this bottom right, this figure. So this is one famous paper called Fat Map by Paul Newman and his colleagues. And you could see that the red dots on the road, the robot tried to navigate in a city and have a few runs. And you could see that the green lines, red dots over here, they are the loop closure detections in the map. Especially when the robot wants to do a large-scale navigation, the loop closure detection it's actually quite helpful to remand the robot at the right place. The formal formulation of the landmark-based map, actually this is from my own paper, my own work. I have been doing this for a while. And the formulation, we can see the camera pulse from x0, x1, etc. To n. We have the landmark locations L1, L2 over here. We have odometry U, U1, UN, etc. And the landmark measurement M1, 2, 3, 4. This is a prior P. And we could imagine that we got odometry somewhere, maybe from visual odometry, maybe from visual or visual inertial odometry over here. So we got this U1. And now the time we are at this x1 over here. When we were in x0, for example, we have a camera. The camera observed a landmark L1, and the measurement is M1. So the measurement could be, if depending on what we want to use, and it could be point-to-point measurement. It could also pulse-to-pulse measurement. If you have a 2D problem, and it could be point 2D to point 2D problem, or point 3D to point 3D. And here we have a measurement 1. Now we are at x1, and we see this L1 again by the measurement 2. This time maybe the measurement 2 is closer to the landmark, for example. And you could imagine that there will be some uncertainty when you got this U1 and M1 and M2. Okay, for example, if you have a landmark and the landmark L1 is an airport tag, and you already have the experience that the airport tag detection will give you transformation, and that would be like a pulse. But depending on your image quality, it could be blurry. Okay, and you may or may not get a correct or accurate estimate, the correct measurements here. But the good thing is that if we have multiple measurements, you could imagine that we go on to x1, 2, 3 to n. For example, we come back to L1. And here is the timing where loop closure happened. So that with multiple, for example, the measurements as well as odometries, you could formulate an optimization problem. You have more observation than you actually need. That will help us to minimize the errors. Okay, so here comes an example. And this is from my own paper, so I definitely want to show you. This is in IRAS 2015. We try to compare. One is to use airport tag as a landmark. The other one is to use text as landmark. And our odometry here is the visual inertial odometry from Tango. Okay, and you can see a red dot over here and a line to the dot. So whenever you see a blue line on the bottom left, this area, that means one measurement. And we try to put the text and the airport tag together and watch here closely. Well, you can see on the bottom left, this one accumulated over time. But you could see some adjustment in the middle and on the right-hand side. So on the bottom left, this is the one just with visual inertial odometry. The middle one, we use the landmark as an airport tag. The right-hand side, this is we use text as landmark. And you could see that the middle one and the right one quite similar, but you could see there are less detections in this graph when we use text as landmark. Here comes a question that if your detector missed one landmark, what's the inference if you miss a landmark detection? Here is the scenario number one. Your detector missed one landmark detection. Okay, and scenario number two, you got the wrong landmark detection. Which one will become a big issue over here? 判断错误，对，假设它有一个 landmark detection 嘛，假设原本是这边有一个蓝色的浅蓝色的点，但是我们有一个 false positive 它出现在右边好了，你觉得会怎么样 ？Yeah, I prepare a diagram like this. So the scenario is that suppose you got the light blue dots, you got a detection there, it should be there, but you got a false positive somewhere else. Then the algorithm will try to put them together as much as possible so that the pulse graph will look like the left-hand side. And even that you have 1,000 landmark detection correctly detected, as long as you have 1 or 2 false positive landmark detection, it will become something like this. There are also some way to deal with this situation, then we call it a robust SLAM. And this is still an active research direction. A basic idea is that you want to see what's the consistency of landmark detections. Okay, so there are some ways to do this. Some good news is that there are many open source implementation, for example, landmark or loop closure detection. And if you want to publish a paper on this research direction, you will have to run this code, compare your own result with theirs. Okay, and the famous one is called FabMap. Oh, that's from Paul Newman and his colleagues. And talking about the implementation, actually not introduce you. You guys must know more about this than myself already. For the map server, we actually run it in the Husk tutorial. Over here, we need 2 files. One is the PGM file. That's a format like a picture. Okay, on the right-hand side over here. And we have another config file, YAML, over here. And you could see some parameters here. So which image you want to include over here. What's the resolution? Okay, when you load this image, you could actually set up the resolution of your occupancy grid. Oh, in map server, the implementation is occupancy grid. There are also some other parameters, for example, the occupied threshold or some other free threshold. So suppose your image over here is kind of grayscale. You could also set some threshold. So something above the occupied thresh, you will consider it as an occupied area, or the other way around. This is the implementation of the map server. And in fact, you could also build some graph on it. So one way we could use Baronial algorithm. You still remember your 2 point, you try to find this line, and this 2 point, you find this line, right? And then you could build this edge, and vertex. Here, you could also, depending on what's the important location in your map, you could also build a graph manually. Okay, so here is another example, about 30 vertices in this graph, and some edge connect those vertices. What can we do with those graphs? This is actually a very important one because you could actually define what's the cost, for example, from node number 11 to number 17. This will allow us to do something very interesting. For example, to do patrolling in a graph. I think this is a very interesting work using multiple. You could also configure a laser rangefinder. Those robots are trying to do the patrolling in a graph. And you could actually try to formulate a problem that team of robots should go to each node as much as possible. So depending on what's your multi-robot behavior, so the graph will become extremely important over here. So far, we have introduced 2D part of the map. So we introduced the occupancy grid. There is a high memory requirements so that we try to use some different data structure like a line map or graph or a landmark-based map. Let's try to move on from 2D to 3D. Okay, so here let me start it with some motivation here. This is something I have done with my colleague Ross Feynman in 2014. And those are the RGBD data from a Tango device. And you could see the top left, that's the RGB frame. Bottom left, that's the depth frame. You could also see the confidence depth map at the bottom right over here. If we put together with the confidence depth map and the RGB, you could kind of reconstruct someone over here. This work, we were using it's called continuous, that's tension of connect fusion. And you may have seen something like this a lot lately, but by that time, 2014, not everyone can do it. So you could see it not only fuse the point cloud and also generate a mesh. And actually, Ross Feynman, he also wanted to create a startup company doing a chocolate. You can like scan yourself and then do a chocolate yourself. This is one interesting application that you could do this called dense 3D mapping. And there are some other exciting things going on here. Here is an example of DARPA challenge. Task here is used the same technique. The red one, there is a higher confidence of that area. And you want to create some confident terrain so that the robot can put their steps on it. Everything we have been mentioned in the class have been putting together somehow. This is by my former colleague, Dr. Maurice Fallon. Let's see a little bit more about Atlas in action. So this is the data were collected in Florida in the DRC finals. And you could see that the sensor is different because now it's outdoor. I may have introduced you like a stereo camera on top of the Atlas, right? So that will also give you the RGBD. But the outdoor, the noise of the sensor is much higher than the Connect sensor. So you could see that from the stereo camera, unstructured, semi-structured terrain could be created so that the robot could actually interact with the world. There are even much more applications. I will just show this video 1 minute over here. And this is done in 2011. So this is a famous algorithm Connect Fusion. There are some very interesting applications here. For example, the augmented reality. You can build like a 3D dense mapping of the environment. You could actually interact with the environment. A little bit scary, right? You know that the VR, AR is quite closely related to robotics nowadays. So today, we definitely want to talk about the representation, like how to represent a map in the world. Let's think about how to do it in 3D. We just saw a few applications of the dense mapping. There are actually some other 3D scene representation. For example, the sparse mapping or some semi-dense 3D mapping. Among those mappings, there are some different purposes. For example, for the sparse mapping, actually many of them are using sparse mapping, and the main purpose is for tracking. For example, those two images are from our ICP lecture. We mentioned that the 3D scan for this street scene, it's more than 200K points per scan. If we can extract some unique features, for example, just 5K, we could highly reduce the computation to do ICP. Let's also think about how to represent the map in 3D. So one straightforward idea is that we just accumulate every single point in each scan. Suppose we also use ICP and get a fairly good pulse estimation, we could put them together. Right? So for example, one scan, we have 200K points. Then two scans, we have 400. And the number of points will increase pretty fast and will explore your memory very quickly. And for the occupancy grid, how about that? Should we use occupancy grid, 3D occupancy grid? So you just mentioned that from the 2D case, we could use a different data structure, for example, lines, to represent the points somehow, right? So what do you think of 3D case? Yeah, sparse It's one way to go. For example, some people use arc-tree, right? You still remember we mentioned that in the ICP lecture. We mentioned about KD tree and arc-tree. 假如说你有一个 cube， 对不对？那你就先切一半一半，一半切3刀嘛，它就变成8个。那假如说其中一个它里面已经空了，或是它里面全部都是solid 或是怎么样，你就不用再切它了。我们就只要处理另外7个 cubes 就好了，对不对？那是 arc-tree. Okay, that's good. So let's take a look at how it works in Connect Fusion. The input is just the raw depth image, and there are some like noise removal in those depth map. And actually, we want to focus on this part. Here is called TSDF Fusion over here. And essentially, you could imagine that it's kind of a 3D occupancy grid. And it's a volume over here. So let's take a look at what's the TSDF. The TSDF is called the truncated sign distance function. Suppose we want to store all point clouds from all frames. Just like what we mentioned, it's way too expensive. Better way is try to do some partition in 3D so that we could have the discrete 3D voxel grid. When we have multiple views, we could try to merge them, try to fuse them together in some way. And over here, the data structure is like a 3D volume. You could see those cells over here. We want to use the TSDF. Some assumptions here. We assume that we have a fairly good cost estimation, for example, by ICP. And we also assume that the object is inside the volume. In other words, the volume is not moving. But you could think of that this assumption will limit our application somehow. So will be like a small scale. The computation is try to compute and store for each voxel. Voxel is like a cube, a small cube in the volume. We try to calculate the distance. The value is from -1 to 1. And we also try to calculate a weight. Okay, so you could just try to remember that for each voxel, you have to store 2 values. One is the truncate sign distance. The other is the weight. And we want to find the zero crossing of TSDF. From those descriptions, it must be very confusing. So let's try to see this by some visualization here. So suppose you have a surface, like a human side face over here. The first thing is to compute a relative distance of each voxel to the surface. You could see that from the left-hand side, you could see as long as the voxel is close to the red surface, it's close to 0. If the voxel is far away from the sensor, the smallest value would be -1. So you could see some of them over here. Here, the purple colors over here, you also see some values, like positive values here from 0 to 1. Okay, and if the voxel is far away from this surface, all of them are 1s. And next step, we want to do ray testing. Essentially, we want to find the zero crossing so that you could see each ray, for example, this one, and we want to find from positive to negative. We want to find the zero crossing here. But I guess this will be much easier to understand what's the TSDF is doing. The next step is that we want to do some integrations among different frames. Each voxels, there are 2 values stored. One is the TSDF value, that's the relative distance. And the other one is the weight. Okay, the weight is kind of the confidence that voxel is a surface or not. Essentially, that's the angle between surface normal and the viewing direction. Okay, and here comes the most important part. The next step is to update the voxels of the global model. So the updating only happened for visible voxels. So if we go back to this figure, we actually don't update those guys because they are not visible. And the next step is that you could see that, for example, if you see it from this angle and from this angle, you may get a maybe slightly different value of each voxel, right? Because your ICP may not be perfect. So here you need to do some averaging over here with the new value. Finally, try to add the new weights to the voxel. This is the basic idea of the Connect Fusion. And the good news is that it's available in PCL, so that, yeah, GPU is required. Like PCL or Caffe, TensorFlow, everything now requires GPU. And just like we mentioned, because the volume is kind of fixed in the Connect Fusion algorithm. Okay, so it is kind of limited to a relatively small scale. When you guys see the video, I just show you a robot walk across like maybe a larger scale, right? Uneven terrain. So it's not the room scaled volume over there. What can be improved over here? So if we need a large scale volume, what should we do? You could also think of, suppose your GPU has 8 gigabyte memory. And for the entire volume, you could actually compute what's the memory required, right? And you could also consider the resolution there. So each voxel, there are two values, right? TSDF distance and weight. Right? So you could do the math and then say, now I have 8 gigabytes. What's the largest scale I could do here? Let me just refer you to this paper called Continuous. So the one you have seen, the robot walking on the stairs, that's relatively small scale. If you are interested, please take a look at Continuous. There are some significant improvements here. And the first one is called Continuous representation. That means that the paper, they figure out some way to move the volume so that it could become a very large scale. And the second part is called the pulse graph, which is what I just showed you, the pulse, odometry, measurement, landmark. Okay, and the good thing is that if you have a large scale, you definitely want to do a loop closure when you come back to the same place. That will dramatically reduce your uncertainty. Mass generation, when you actually find a surface and you definitely want to save it in a more memory efficient way, for example, a triangular mesh. Continuous, the author, they opened a startup company, but later I think they are acquired by Facebook. Very amazing. Okay, and finally, we also know that ICP may not be the best way to do the odometry. So in this paper, they also try to use FOVIS to use the visual odometry and in order to get the camera pulse. And the best part is that it's open source now. So when his name is Tom Whalen, and when he open source this stuff, we were surprised that, oh wow, you open source this. Yeah, people are excited about this work.